Let's look at specific albedo numbers for various surfaces. Fresh snow and ice can be 60 to 90%. Old or melting snow is lower, darker, 40 to 70%. Clouds depends on their high clouds, low clouds, deep clouds, and so on. 40 to 90%. There is a large range, and in fact, in global warming, one of the most challenging problems is to figure out whether clouds will increase the albedo and try to cool down the earth, or whether they will just trap more heat in response to increased greenhouse gases. Okay, desert sand is more reflective than soil. Tundra, the forests at low vegetation at high latitudes, is got slightly high albedo. Grasslands, forest is darker, and water also darker, depends on the angle of incidence, but nonetheless generally it's highly absorbing. The distribution of radiation with season over latitudes in a zonal mean sense, at the top of the atmosphere for example, can be looked at in terms of the seasonality. In the current configuration of the Earth's orbit around the Sun, we have the equinoxes in March and September, where the Sun is over the equator, so there is equal length of night and day at every latitude. And at the boreal summer solstice, we have the Sun reaching the Tropic of Cancer, pausing for a moment, that's what solstice means, and then start traveling back, right? And December solstice, the Sun is down at the Tropic of Capricorn and then heading back north. So the seasonality depends on the tilt of the axis and the axis pointing towards the Sun or away from the Sun. So you can see the distribution from the south to north. Obviously in the boreal summer winter of January, February months, you get no sunlight here. In spring you can get 24-hour sun in some parts within the Arctic, within the high latitudes to the Arctic Circle. You can get 3 months of summer, 24-hour daylight, and 3 months of complete darkness, depending on where you are, right? So similarly here in the southern hemisphere, summer and winter. And in the middle you have this seasonality of distribution of the radiation, peaking in summer months. Clouds, monsoons, other things actually give you higher radiation during off season. Not summer is not the highest radiation month necessarily. Okay, it depends on where you are and so on and so forth. And the southern hemisphere summer here, of course. Okay, this distribution matters because all that energy is used to evaporate water from the ocean, from land, from rivers, lakes, melting glaciers, and the evaporated water is caught in the warm rising air, condensation, rainfall. Almost all of it falls back on the ocean as rain. Some of it is made onto land as rain and snow on the mountains, etc. I think this is 86% falling back and about 14% going over as clouds and atmospheric rivers and so on. Okay, so the melting of the snow and ice will add together with the rain to produce a runoff, which can go into groundwater, go into soils and rock fractures, etc., and produce some runoff. These are faster time scale surface runoffs, and these are longer time scales or slower time scale groundwater runoff. So it turns out that humidity is the big nonlinear factor because its saturation density in the air depends on temperature. Obviously dry airs like at high latitudes are bone dry, so they are very low in humidity, down to 0, and the tropics, warm tropics, hold much more moisture. You can see the saturation density of 30 gram per meter cube. This is important because water vapor is also a greenhouse gas, and if global warming increases temperatures, it will hold more moisture. Moisture will increase the warming, so there is a positive feedback. So that's our first example of a positive feedback. But water vapor is a feedback greenhouse gas in the sense if you cool the temperature it drops off, if you warm the temperature it increases. Okay, so something to remember. It is an important greenhouse gas, but it's a feedback between the water vapor, its greenhouse effect, and atmospheric temperatures. But it has a nonlinear exponential dependence on a temperature, and that makes a difference because with each degree of warming you will get 7% increase in humidity. Then we'll see that there is another concept called relative humidity, which is specific humidity that's actually present divided by saturation humidity, which means at a given temperature, if you completely saturated the air with its full capacity corresponding to that temperature, then that's saturation humidity. So saturation humidity also increases as temperature increases, and specific humidity increases. So relative humidity may not increase, especially on the ocean where you have infinite moisture available for evaporation. But this can change on land, because on land you don't have a infinite supply of moisture, plus moisture is often brought in from the ocean. Okay, so this complicates things, and the best thing to remember is that the water vapor in the atmosphere is a very nonlinear quantity that makes for interesting feedbacks.